Welcome back. All right, so let's take a look at a couple of the things that we just had here. So Theorem 210 said that the probability of, this is the multiplicative rule, the probability of the intersection of A and B is equal to the probability of A times the probability of B given A. And definition 211 says if A and B are independent, then the probability of B given A is, well, if A and B are independent, then that's just the probability of B. And so we can combine these things, and then we would ourselves just derive Theorem 211 for us. Theorem 211. Right? What are we going to do here? Basically, probability of A intersect B, if they're independent, then this B intersect A right there is just the probability of B. And so we're just going to substitute that in as an alternative for independence. A and B are independent events. Independent. Independent. Let's try that again. Are independent if and only if the probability of the intersection A and B is equal to the probability of A times the probability of B. Clarify that equal sign, equal to that. Okay. Nice. Good. Good. This extends, I'll mention, this extends to multiple events. In a very natural way. I'll say this extends naturally to 3 or more events. In the sense that you can look at 3 events, A, B, and C, and if those events are independent, then the probability of the intersection of A, B, and C would just be the probability of A times the probability of B times the probability of C. Okay. I also want to mention right now Theorem 212 and then show a little bit of interplay between these two things here. Theorem 212 says the following. It says the probability, speaking of extending to more than 2 events, let's say we have A1 intersect A2 intersect A3 intersect yada yada yada. Let's say we are intersecting K events. That this is equal to the probability of A1, this is an extension of the multiplicative rule, times the probability of A2 given A1, times the probability of A3 given A1 intersect A2, times the probability of A4 given A1 intersect A2 intersect A3. Let's straighten that up here real quick. Got my A's and my intersection symbols there. And I think we get the idea here though, right? Times all the way to the kth event, A sub k, given A1 intersect A2 intersect yada yada yada, A sub k minus 1, the most previous event. All right. So we have that. That's sort of an extension of the multiplicative rule here, okay? But what I want to kind of, again, tie these things in together, right, is think about if we know these are independent, right? If all are independent. Geez, I cannot write the word independent down very well. I think this is why subconsciously I tend to write just and stop here and abbreviate it. If all these events are independent, right, then well, let's just think about this. If all these events are independent, then what do we know here? Well, we know the probability of A2 given A1 would just be the probability of A2, right? So that would just be probability of A2 if A1 and A2 are independent, right? Now, independence is a little bit more loose in terms of what we might be comfortable with when you start thinking about A3 given an intersection, right? But just take the true definition of conditional probability. This should be the probability of the intersection of all three of these to intersect A3, right? Divided by the probability of the intersection. Okay, but we know that these are independent, so this is going to be A1 times the probability of A2 times the probability of A3 divided by, again, by independence, based on Theorem 211, probability of A1 times the probability of A2, and so all of a sudden you've got this cancels, this cancels, this cancels, this cancels. It's just the probability of A3, right? Right? And so on and so forth. And we can continue down that fashion, right? We can continue down that fashion, okay? So with those two theorems in mind, then I want to just do a couple of examples here, okay? So let's take a look at something that has multiple independent events happening. Okay, just to clarify, Theorem 212, this applies for all cases, even when they are not independent, right? This is true in general. This is true in general. You have these conditional events. If they're independent, this simplifies down a lot. But if they're not independent, we still get to use that, okay? We still get to use that. And so let's go ahead and start with that. Let's say 3 cards are drawn in succession. 3 cards from a standard deck of playing cards are drawn in succession. So in succession means one at a time. One at a time. Without replacement. Without replacement from a standard deck of 52 cards. Standard deck of 52 cards. Let's go ahead and find the probability of A1 intersect A2 intersect A3 if A1 is the event that the first card is red ace. The first card is a red ace. A2 is that the second card is a 10 or a jack. And A3, the third is greater than 3, but less than 7. Greater than 3, but less than 7. Okay. Let's take a look at this. According to Theorem 212, we want the probability of A1 intersect A2 intersect A3. Okay? And we don't know if these are independent, so we cannot assume that they're independent events. So we need to use this theorem in its full capacity. So we're looking at, for the probability A1 intersect A2 intersect A3, this is just the probability of A1 happening, times the probability of A2 given A1, times the probability of A3 happening given A1 and A2 have occurred. Right? That would be the full application of that theorem. So let's see here. What's the probability of A1? First card is a red ace. There are 2 aces that are red out of 52 cards in the deck. 2 out of 52. Now, what is the probability that the second card is a 10 or a jack, given that you've gotten a red ace? Well, first of all, you've pulled a red ace out of the deck. So there are only 51 cards left to choose from. Now, how many of them satisfy A2? Well, 10 or a jack, there's 4 10s and there's 4 jacks. And since the first card was a red ace, you're not lowering your sample pool from successful events. So there are still 8 successful options to pull from, but there's only 51 cards left in the deck. So that would be 8 out of 51. How about the probability of A3 given A1 intersect A2? Well, first notice that if you've drawn a red ace and a 10 or a jack, there are only 50 cards left here. Because remember, this is done without replacement. Now, a red ace and a 10 or a jack, neither of those events are affecting the numbers 3, 4, 5, 6, or 7. Right? So greater than, I should be clear, greater than 3, that means we could have a 4, a 5, or a 6, less than 7. Not including, these are not including 3 or 7, right? Greater than or less than. So this is 4, 5, or 6. There are 3 options of each left for a total of 12. So there's a 12 out of 50 shot that happens. So then this product then is 2 out of 52 times 8 out of 51 times 12 out of 50. And we can run that through a calculator. That should be 8 out of 5,525. 8 out of 5,025. All right, here we go. Last example. Let's say we are looking at an electric system. Sometimes you'll see the book likes to throw these electrical diagrams out and works with them. An electrical system consisting of 4 independent components. 4 independent components shown below. I'll draw a sketch for you here in a second. Works only if A and B work and either C or D work. Either C or D work. So you need to have A and B work, and then either one of, or at least one of C or D would work. If both work, that's just fine. Okay, so here's the component A. This goes to component B, right? If you're traveling along this, you need these both to work, and then we split. I'm not an electrical engineer. I don't know if these are running in parallel. Is that what this is called? Might be running in parallel. Not quite sure. So you have C and D. You need at least one of these to work to make it out to the other side, right? Okay. Now, the probability that each of these works will give inside the boxes here 0.9 and 0.9 for A and B. Say there's an 80% chance that either of the components C or D work. All right. Let's find the probability that part A, the entire system works. Let's see here. Probability the entire system works. Okay, well, let's write this out in our set notation, what probability we're looking for. We need A and B to work. So we need A to work and B to work. That's an intersection. And either C or D. Either C or D will work, grouping those in parentheses. So this is A intersect B intersect either C or D. All right. So far, so good. Okay, let's take a look at this. It's important here to note these are 4 independent components. 4 independent components. So we're going to heavily make use of theorem to 11 and extend that. So these are independent, so we don't need to really do any conditioning. This is just the probability of A times the probability of B times the probability then of C or D working. C or D here, okay? And notice with independence, right? Notice that this is not equal to the probability of C plus D via independence, right? Or C times D. The independence is, let me rephrase this. Maybe we'll do times here, right? This is an or. Independence is for the probability of C intersect D. We need the intersection. We need the intersection in order to pull that independence out, okay? Is there a way we can write C or D as an intersection of those events? Well, yeah. Think back to some of those laws that we had. Think back to the De Morgan's laws and other things like that, right? How can we introduce something we can use De Morgan's laws in? Well, if you look at the complement, C or D, probably a C or D, is that not the same thing as 1 minus the probability of C or D complement? Right? 1 minus the complement probability is exactly the probability that we would want. Now, why did I introduce this idea? Because C or D prime, then I can use De Morgan's laws here, C or D, and sort of distribute that into that. This is going to be equal to the probability of A times the probability of B times 1 minus the probability of C prime intersect D prime, right? And that is De Morgan's laws. If you don't remember, we can go back to our notes. It's the end of 2.2 in the events, De Morgan's laws. A or B prime is A prime intersect B prime. De Morgan's laws. So we have those there, right? So introduce the complement in order to get the C or D prime component. Once I got the prime component on the or, I can use De Morgan's laws to change that to an intersection, okay? But C and D are independent. So this is 1 minus probability then a C prime times the probability of D prime. And what do we have now? Well, probability of A is 0.9 based on the diagram. Probability of B is 0.9 based on the diagram. And then 1 minus C prime or D prime. What is probability of C prime? Well, if the probability that C works is 0.8, what's the probability that C doesn't work? Well, 1 minus that would be 0.2. And it's going to be the same thing for D as well. And so we have 0.9 times 0.9 times 1 minus 0.2 times 0.2. Run that through a calculator, and we should get about 0.7776. All right. Part B. This is the last part here. Let's find the probability that component C does not work. Try that again. Component C does not work, given that the entire system works. Given the entire system works. This is a conditional probability, right? Find the probability C does not work given the system works. How do we find this conditional probability? Well, let's go ahead and look at using the definition here, right? This would be the probability of the intersection. So this is the probability then that C does not work and the system works divided by the probability of the given, which is the probability that the system works. All right. Let's see. I can start translating these English statements into some event statements. What's the probability that C does not work and the system works? Well, if the system works, that had to be A intersect B. C does not work, so that's intersect C prime. But if the whole system works, it must be then that D is working, right? Because in order for this to work, you have to have either C or D work. So if we know C is out, D has to be in. So there's our numerator. And then the probability that the system works is A intersect B intersect C or D, which we've already done this denominator, right? We know that the denominator is 0.7776 based on the last question. We just answered that, part A. What about the numerator? Well, these are all independent. So this is the probability of A, which is 0.9, times the probability of B, which is 0.9, again, based on the diagram here. A is 0.9, B is 0.9. And then C prime is 0.2, and the probability that D works is 0.8. And so we run that number through the numerator in a calculator, divided by the 0.7776, and I've got something about 0.1667, if I round that off to 4 places there. All right. So that's going to do it for us here. As usual, please post comments, questions, concerns in the discussion thread below, and we look forward to seeing the chat down there.